In this video, I'm going to be showing a fundamental application of binomial expansion in calculus. So let's start with proving this to be true. You will come to realize how important binomial expansion is in proving this using first principle of differentiation. So I'm going to start with y equals ax raised to the power n, implying that y with an infinitesimal change in y, that is y plus change in y, will be equal to a in bracket x plus change in x all raised to the power of n. And this would imply that if you make change in y the subject of formula, you are going to have a x plus change in x all raised to the power of n minus y. Now, change in y obviously will be equal to a x plus change in x all raised to the power of n minus what y is. We are told y is ax raised to the power of n. So I'm going to bring that here. Now, x plus change in x all raised to the power of n can be simplified or expanded using binomial expansion. So what I'm going to do will be to bring the problem here. Okay, so change in y will be equal to ax plus change in x all raised to the power of n minus ax raised to the power of n. Now let us expand. Now, we are told from binomial expansion that the coefficients are combinatorial in nature. So I'm going to put here n combination 0, x raised to the power of n, change in x raised to the power of 0, plus n combination 1, x raised to the power of n minus 1, change in x raised to the power of 1, plus n combination 2, x raised to the power of n minus 2, change in x raised to the power of 2, plus ellipsis plus n combination n minus 1, x raised to the power of, at this point in the expansion, since we are referring to the second to the last term, you would have this to be 1. And this will be change in x raised to the power of n minus 1. And adding the last coefficient, you have n combination n, x raised to the power 0, change in x all raised to the power of n, and that completes the expansion. And I'm going to bring this term in, minus ax raised to the power n. Now the next thing you're going to do will be to simplify. A in bracket n combination 0, anything combination 0 is 1, so I'm going to put 1 here, times x raised to the power n, times anything raised to the power of 0 is 1, so that will be 1, plus n combination 1 will give you n, anything combination 1 gives you n. So I'm going to have this, and this is change in x, because change in x raised to the power 1 by indices is change in x, plus anything combination 2 will give you, when you simplify, rather than do this, just have n times n minus 1 all over 2 factorial, which is 2, and this will be x n minus 2, change in x raised to the power of 2. Now please, I would advise you visit my video on permutation and combination. Now this will continue until n combination n minus 1, and anything combination 1 short of itself is that thing. So I'm going to have here n in bracket x raised to the power 1, which is x, and you're going to have change in x raised to the power n minus 1. Then anything combination itself is 1, so I'm going to have 1 here. X raised to the power 0 is 1, times change in x all raised to the power of n, and all this will be in bracket minus axn. Now, this is a very good application of binomial expansion in calculus, because without this expansion, you can't solve this problem. So what I'm going to do next will be to further simplify, and this will give me 1 times x raised to the power n times 1 is x raised to the power n, plus nxn minus 1, change in x, plus n minus 1 divided by 2, x raised to the power n minus 2, change in x all squared, plus ellipsis nx change in x raised to the power of n minus 1, plus 1 times that will give you change in x raised to the power of n, okay, minus ax raised to the power of n. Now, on expanding, take note, your a's would open up this bracket. So let's use our a to open up this bracket. You have ax raised to the power of n plus n times a, which is an x n minus 1, change in x, plus n, let's put our a first of all, a times this will give you a n minus 1 divided by 2 x raised to power n minus 2 change in x all squared plus ellipsis plus a n x change in x raised to power n minus 1 plus a change in x raised to power n minus, okay, since let's leave that open, rather, axn. Now you will notice that this can cancel this and the problem reduces to a n x raised to power n minus 1 change in x plus a n minus 1 all over 2 x n minus 2 change in x all squared plus ellipsis plus a n x change in x n minus 1 plus a change in x raised to the power of n. Now at this point we have gotten a simplified expression for change in y, the infinitesimal change in the dependent variable. Now when we get the gradient function change in y over change in x, you will end up dividing everything here. Every term in the right hand side will be divided by change in x. Now if you divide this side by change in x, you will end up having a n x raised to power n minus 1. If you divide the next by change in x, you have a n minus 1 over 2 x raised to power n minus 2, and 1 change in x will remain because 1 cancels off, plus a n x change in x. This would decrease by 1, so this will be n minus 2 plus a change in x. Instead of a change in x raised to power n, you have n minus 1. So doing that implies that we've gotten the gradient function. Now in calculus, please take note, dy dx is the limiting value of the gradient function. So we have to take dy dx, which is what we want to obtain, and dy dx is you taking the limiting value as change in x tends to 0 of the gradient function, which is change in y all over change in x. If you do that, it implies that you would have to put 0 every place you have change in x. So the only term that has no change in x is this first term. Putting change in x here as 0 implies it will multiply all this, giving you 0. Putting change in x here as 0 implies it will give you 0 here. Putting change in x as 0 here implies it will give you 0. So the only term remaining will be a n x raised to power n minus 1. Thank you very much for watching this video. Please do like, share, subscribe to the channel, and endeavor to join my community on YouTube. It's going to be a very good ride along with you as a member of my community. Stay blessed.